Before we explore some of the mathematical equations behind the Coulomb force, I want to go back to the mathematical relationship between two masses when it comes to gravity, because the structure of the mathematical relationship between two masses with respect to gravity is very similar to, say, two charges when working out the mathematics of the Coulomb force. So if we have two masses, say M1 and M2, and we've got some distance that we'll call R between them, then we will say that the force of gravity is going to be equal to some gravitational constant G multiplied by M1 multiplied by M2 and divided by the square of the distance R between them. And this G is defined when you see three equal signs, that's defined 6.674 times 10 to the minus 11. And then the units on this are newtons times meters squared divided by kilograms squared. It's important to keep tabs on units. I'll say a little bit more about this in a second. So if you look at, say, the units, when I put in brackets here, it means we're going to do a unit analysis. So the G has units of newtons times meters squared over kilograms squared. And then we've got a kilogram for the first mass. We've got a kilogram for the second mass. And then we've got distances in units of meters for SI, and so we'd have meters squared. So let's look at the dimensions here. We have in the numerator a meter squared, but also in the denominator we have a meter squared. So I'm going to cancel the meter squared out. That just would become unity, i.e. 1. And then look at this. We have a kilogram times kilogram, which is kilogram squared, but then we have a divide by kilogram squared. So that just becomes 1 as well. And you see how the units for gravity is just newtons. So it makes sense that the gravitational constant is going to have units of newtons times meters squared divided by kilograms squared. And so remember, with gravity, gravity is an attractive force. So if we were just to think about mass one would experience a force that is in the direction of mass two. And similarly, mass two is going to experience a force in the direction of mass one, and it's equal and opposite. And it's equal to what you see up there in blue. And the gravity can only be an attractive force. So the force on mass one by mass two is equal and opposite the force on mass two by mass one. But here's the key. The structure of this equation is one in which in the numerator, you have the multiplication of the two masses involved. In the denominator, you have the square of the distance between the two masses, and you have this constant. Okay, so now let's instead say that we've got charges. So I'm going to say that I've got some charge, and we'll call it Q. And I'm going to say that there's another charge, and this is sometimes called a test charge, where it has the symbol Q with the subscript 0, or sometimes as it's called Q naught. And so there's some distance R between these two charges. And so it turns out that the Coulomb force, so I'll say that FC is equal to, now we're going to use the symbol K, and then we're going to have the charge Q, and then we're going to have the other charge Q naught, and then we're going to divide by R squared. Does that look similar? You see that it has the same structure where in the numerator, now you're multiplying by the charges, and now you're divided by the square distance between them. Now the difference here is that the Coulomb constant K is defined as 8.988 times 10 to the 9 newtons times meters squared divided by Coulomb squared. If you look up in the right with the blue with the gravitational constant and then look at the K in the orange, do you see some similarities there in terms of units? The numbers are different, but do you see some similarities in terms of units? Let's do a dimensional analysis for the Coulomb force. So that is going to have the dimensions for the Coulomb constant K, which is newtons times meters squared divided by Coulomb squared. And then we've got two charges, Q and Q naught. So that's going to be Coulomb, and then R squared. Remember the SI unit of distance is the meter. So we'd have meters squared. So once again, we see there's a meter squared downstairs and a meter squared upstairs. That becomes unity. And then we have a Coulomb times a Coulomb, which is a Coulomb squared divided by a Coulomb squared, unity. And so what do you know? Again, you have units of newtons. So I'm hoping you can see the similarities in the structure between the gravitational force and the Coulomb force. But a big difference is that the gravitational force is always attractive. It's always, say, mass 1 being gravitationally attracted towards mass 2, and mass 2 being gravitationally attracted towards mass 1. But when it comes to the Coulomb forces, it depends on what the sign of the charges are. So let's say I got my Q and I got my Q naught. Now, if Q is positive and Q naught is positive, then like charges repel. So that would mean that Q naught would experience a force in this direction, and Q would experience a force in this direction. Just like gravity, it's equal and opposite. But here's the thing. Let's say that instead of positive Q, let's say that instead we have negative Q. Now you have opposites, and it turns out that opposites attract. So now what's going to happen is that the minus Q is going to be attracted towards the plus Q. So it's going to want to go in this direction. And meanwhile, the plus Q is going to be attracted towards the minus Q. And it's going to go that direction. Again, it's equal and opposite, but you see how sometimes with the Coulomb force, you have opposites attracting. And by the way, this could have been minus Q naught and plus Q, and you'd have the same thing. You'd have the opposites attracting. Or if you have the similar charges, whether Q and Q naught were both positive or Q and Q naught were both negative, they would repel each other. So I hope you very much see there's a very similar structure between the Coulomb force and the gravitational force. But you have the additional consideration with the Coulomb force of whether the charges are positive or negative, because with masses, gravity is always an attractive force. One last thing that I want to point out. Look at the gravitational constant G, which is in blue, and look at the Coulomb constant K, which is in orange. So K, 8.988 times 10 to the 9 Newton times meter squared plus Coulomb squared. So in comparison with G, which is 6.674 times 10 to the minus 11 newtons times meter squared times kilograms, or divided by kilograms squared. So let's just roughly say that like 8.988 and 6.674. 8.988 is a little bit bigger, but they kind of wash each other out. What I really want you to look at is the 10 to the 9 versus the 10 to the negative 11. So if I was to take a ratio, if I was to say K divided by G, then I would have of order of magnitude 10 to the 9 divided by 10 to the minus 11. Now, when you are looking at exponents, and so if you have something to the something power divided by something to the something power, what you do is you're actually going to subtract the exponent at the top from the exponent at the bottom. So you would have 9 minus 11, which is the same thing as 9 plus 11, which is to say that the ratio of k to g is of the order of magnitude of 10 to the 20. Okay, to put it in perspective, a billion is 10 to the 9. So 10 to the 20 would be 100 billion billion. The ratio of the Coulomb constant to the gravitational constant is roughly 100 billion billion. This is to say that the electrostatic force between charges is fundamentally way stronger than gravity. And so it turns out that like you can have much smaller things still have massive forces exerted on each other. When it comes to gravity, which is a relatively weak force, as I hope you can see now compared to the electrostatic force, you need really massive stuff in order for gravity to really start playing a role in the universe. In other words, you need things like stars and planets and galaxies and clusters of galaxies. When you have massive, massive objects, yeah, gravity is definitely going to be something that needs to be considered. But when you get to the world of the really small stuff, the electrostatic force, for example, is going to be so much more dominant with how those tiny objects are going to move through the universe and exert forces on each other.